Welcome to another Mathologer video. The golden spiral over there is one of the most iconic pictures of mathematics. The background of the picture is this special spiral of squares. And the golden spiral itself is made up of quarter circles, inscribed into these squares. Overall, this quarter circle spiral is a very close approximation of the true golden spiral, which is a logarithmic spiral that passes through these blue points here. This spiral here. Pretty good fit, Our golden spiral picture captures some of the amazing properties of one of mathematics superstar, the golden ratio phi. However, the one feature that this picture is most famous for is, sadly, just a mathematical urban myth, pushed and propagated by lots and lots and lots of wishful thinkers. These people, I call them phinatics, will assure you that the spiral that you see in Nautilus shells are golden spirals, which is simply not true. Same thing for spirals in spiral galaxies, cyclones, and most other spirals found in the wild. What is true is that, just like our quarter circle spiral, a lot of the spirals you observe in nature are approximately logarithmic spirals. However, there are infinitely many different logarithmic spirals. And most of the logarithmic spirals found in nature are not even remotely golden. In fact, most of the pictures that are supposed to prove the golden nature of naturally occurring spirals are arrived at by roughly fitting a really thick golden spiral to some suitably chosen and doctored picture. Having said that, sometimes the spiral patterns that we observe in nature, like for example those in flower heads, do have a connection to the golden ratio. However, in general, not even the spirals in flower heads are golden, and the connection is established in different non-spiral ways. If you're interested, I've linked to some articles that debunk a vast portion of the golden spiral in nature story. Phinatics, sorry to disappoint. What I'd like to do in the following is to focus on some true and truly amazing features of this picture, which even a lot of mathematicians are not aware of. What will be important for us about this picture is the curious spiral of squares at its core. In fact, as far as today's story is concerned, the sole function of the golden spirally spiral is to highlight this square spiral. It turns out that not only the golden ratio, but in fact every positive real number has an associated square spiral. For example, here's the spiral of root 2. Hands up, who has seen a green golden spiral before? Anyway, these square spirals, which can be finite or infinite, are very easy to construct and provide a wealth of insight into the nature of numbers. For example, I'll show you that if you look at root 2's square spiral in just the right way, it magically morphs into a so-called infinite descent proof of the irrationality of root 2. In fact, I show you a simple characterization of the irrational numbers in terms of their square spirals, and use this characterization to pin down and visualize the irrational nature of many famous numbers. To finish off, I'll show you how the square spiral of a number is really the geometric phase of the so-called simple continued fraction of that number. Those guys here. Anyway, ready for some really amazing and beautiful mathematics? Let's go. Okay, to start with, let me show you how the square spiral of a number is constructed and why, if the resulting spiral is infinite, the number has to be irrational. I'll first focus on the number root 3. To construct the spiral, we start with a root 3 rectangle like this one here. A root 3 rectangle is a rectangle with sides a and b, whose aspect ratio a over b is equal to root 3. Trivial but important observation: if you scale a root 3 rectangle, you get another root 3 rectangle. Now here's the first square of the root 3 square spiral. Here's the second square of the spiral, the third, the fourth. The rule is that the next square is the largest square that fits into the remaining green area, fitted in such a way that it continues the right turning spiral. So next is this, then this, and this, and so on. Pretty straightforward, right? Let's quickly go back to the beginning and count the number of squares of each size that we come across in this spiral. Okay, first square again. There's only one square of this size. Next, also only one square of this size. Next, and two of those, okay. Then one, then two again. In fact, from this point on, things repeat. So 1, 2, 1, 2, 1, 2 forever. Neat, One way to convince ourselves that things really repeat is to show that this blue rectangle here is also a root 3 rectangle, just like the green one we started with. This means that new squares fit into the blue rectangle in exactly the same way as they do in the starting green rectangle. And so the pattern repeats. Okay, let's show that this blue rectangle really is a root 3 rectangle. Remember that we started with a root 3 rectangle, and so the ratio of the sides is root 3. Put the first square in, and so the dimensions of the remaining green area are what? Well, short side on top has length a minus b, and the long side, obviously, b. Put the next square in and calculate its side length in exactly the same way. Now the third square. And now let's check that the aspect ratio of the blue rectangle is really root 3. This aspect ratio is what? Well, this. Now some straightforward algebra. Divide both the numerator and denominator by b. That does not change the ratio. But remember, a over b is equal to root 3. The standard trick to get rid of the root in the denominator is to multiply the bottom and the top by 2 plus root 3, like that. Just in case you have not seen this trick in action, let's highlight the denominator. The highlighted product is of the form u minus v times u plus v, which of course is equal to u squared minus v squared, which in this case is 2 squared minus root 3 squared. And so you can see the square root in the denominator vanish. Remember this clearing the denominator of roots trick. It really comes in handy very often in maths. Anyway, now just go on algebra autopilot and you'll see that the whole expression simplifies to root 3. Wonderful. At this point, we are ready to draw a couple of pretty amazing conclusions. Let's start by using our square spiral to prove that root 3 is irrational. This also ties in nicely with what I did in the last video. Okay, if root 3 was rational, that is, if root 3 could be written as a ratio of positive integers a and b, then the rectangle with sides a and b would be a root 3 rectangle. Now we just calculated the lengths of the sides of the first couple of squares, right? Now since a and b are supposed to be integers, these three side lengths, b, a minus b, and 2b minus a, would have to be integers as well. In fact, it's very easy to see that this continues. The side lengths of all the infinitely many squares in our spiral must be some integer multiple of a or b minus some other integer multiple of b or a. Like down there, integer times a minus integer times b. This implies that all the side lengths of all the squares all the way down are positive integers. But, and regulars have heard me say this a lot, this is impossible. Why? Well, the infinitely many squares in our spiral shrink to a point. And therefore, they must eventually have side lengths smaller than the smallest possible positive integer 1. The only way to resolve this contradiction is to conclude that the assumption we started with, namely that root 3 is a ratio of positive integers, is wrong. And so we conclude that 3 is irrational. That is a really, really pretty proof. Don't you agree? But it is much more than that. Why? Because all sorts of things we've just said stay true beyond the special case of root 3. For example, it's really easy to see that if we start with any rectangle with integer sides, and if we remove squares according to our recipe, then all those squares in the spiral must also have integer sides. This means the same proof by contradiction shows that any number with an infinite square spiral must be irrational. So for example, the golden ratio phi is irrational because its spiral is also infinite. Now, here's a really pretty way to picture what we've accomplished. The essence of our proof by contradiction is called an infinite descent, because our assumption that a rational number has an infinite spiral implies the existence of an impossible infinitely descending or decreasing sequence of positive integers. Very nice. But also notice that you can actually see the impossible infinite descent in the spiral by interpreting the squares as steps of an ever-descending spiral staircase. There's our infinite spiral staircase and the footsteps of someone going for the infinite descent. What's going to happen when they reach the bottom, what do you think? Anyway, to round off this part of the video, just remember that if we can show that a number has an infinite square spiral, then we've also shown that this number is irrational. So what about the spiral of a rational number? Well, obviously it cannot have an infinite spiral. That is, its spiral must end after a finite number of steps. But how does it end? Well, let's have a look at an example. The aspect ratio of the rectangular frame of this video is 1920 over 1080. That means that this rectangle is a rectangle that corresponds to the rational number 1920 over 1080. And so, as you can see, the square spiral of this number consists of only 7 squares. So the spiral ends because when we place the 7th square, the rectangle we started with is completely covered. There is no space left for an 8th square. Here's an interesting fact. The side length of the smallest square in this finite square spiral is the greatest common divisor of the numbers 1920 and 1080. Puzzle for you. Show that this is true in general. Second puzzle, for those of you in the know, which super famous Greek mathematician is responsible for some closely related mathematics? Okay, so we can be sure that the square spiral of a rational number is finite. How about going the other way? Is it also true that every finite spiral comes from a rational number? Well, let's see. Say I give you a finite spiral like this one there. Here's how you can determine its aspect ratio. First, we scale things so that the smallest square has side length 1. Then it's clear that the next larger square has side lengths 1 plus 1 plus 1 is 3. Then we can see that the largest square has side lengths 3 plus 3 plus 1 is equal to 7. And finally, that the top side of our rectangle is of length 3 plus 7 is equal to 10. And so our rectangle has aspect ratio 10 over 7. And of course we can do exactly the same for any finite spiral to show that it corresponds to a rational number. Neat, huh? Okay, so that means that the rational numbers are exactly the numbers with a finite spiral, which then also implies that the irrational numbers are exactly those numbers with an infinite spiral. That's a pretty amazing characterization of rational and irrational numbers, don't you think? Definitely made my day the first time I read about this. Now, to actually use this characterization of irrational numbers to prove that a particular number, such as phi, is irrational, we somehow have to show that its associated spiral is infinite. The way we were able to show this for root 3 was by recognizing that the square spiral repeats. In turn, this was possible because we were able to show that while building the spiral, we come across rectangles with the same aspect ratio. Now, it's very easy to see that this also happens for the golden ratio phi. In fact, this repeating property is part of the definition of the golden ratio. That is, a rectangle is golden if, when you cut off a square like this, you end up with a scaled down version of the original. So, since things repeat, after cutting off one square, this also means that phi has the simplest possible square spiral, with every square size occurring just once and the associated sequence of integers being all ones, like that. Anyway, just remember, things repeat for phi. So next time someone asks you why the golden ratio is irrational, just point at the closest golden spiral and say infinite descent in an ominous voice. Okay, as a final repeating example, here is root 2. And here's a nice little root 2 factoid that I actually did not know myself until recently. All these pink rectangles are root 2 rectangles, right? Of course, an A4 piece of paper is basically a root 2 rectangle. What this means is that if you fold the paper in half, you get a scaled down version of the original, that is, another root 2 rectangle. But did you know that you also get another root 2 rectangle when you cut off 2 squares like this? There, another root 2 rectangle. Very cool. Maybe not earth-shatteringly cool, but I enjoy little maths moments like this almost as much as the really deep stuff. Okay, at this point it's natural to ask for which numbers this works. So which numbers have a repeating spiral? Well, the examples so far were phi, root 2, root 3. So all square rooty numbers. In fact, it turns out that the numbers with a repeating spiral are exactly the numbers of this type. And when I say of this type, I mean all positive irrational numbers that are roots of quadratic equations with integer coefficients. These numbers are usually referred to as quadratic irrationals. Now, the fact that a periodic spiral implies that we're dealing with one of these rooty numbers is pretty easy. And was first shown by one of the usual suspects, Leonhard Euler. On the other hand, showing that every quadratic irrational has a repeating square spiral is not super hard, but it's definitely a little bit fiddly. So let me just show you a sketch of the easy direction. Periodic spiral implies quadratic irrational. So let's say x is a number with a repeating spiral. Then in this particular x rectangle, all side lengths of the resulting squares look like this. So integer times x minus another integer, or integer minus another integer times x. This means that the aspect ratios of the rectangles that we come across during spiral building are ratios of expressions like this. For example, we could have something like that. Now we said the spiral repeats. What this means is that two of these aspect ratios have to be the same. But obviously after multiplying through with the denominators, any such equation simplifies to a quadratic equation. And so x as a solution of this quadratic equation is a quadratic irrational. Easy peasy. Lemon squeezy? Oh, well. Puzzle for you. What's the solution to the equation over there? And what do all the coefficients in this equation have in common? A coincidence? I don't think so. Okay, now at the start of this video I claimed that the square spiral of a number is really the same thing as the simple continued fraction of the number. To explain this correspondence, let's have another look at the root 3 spiral. Okay, here comes the magic. To get the continued fraction, you just take the sequence of numbers of squares of each size at the top and do this. So root 3 is 1 plus 1 divided by 1 plus 1 divided by 2 plus and so on. Very cool, right? But how does this work? Well, let me finish off this video by explaining. What I'll do is to run the standard algorithm for generating the infinite fraction and our algorithm for building the spirals side by side. This will make it clear why we are getting the same sequence of green numbers. Okay, root 3 is equal to 1.7320 and so on. Let's rescale the short side of our root 3 rectangle to make it length 1. Then the long side is equal to root 3, that is 1.732 and so on. Okay? How many squares of side length 1 can we fit? Well, obviously just one, the integer part of root 3. Next, let's have a look at the rectangle that remains. Let's rescale everything so that the short side of the green rectangle becomes 1. The scale factor that does the trick is 1 over 0.7320. Up on top we can also do something. We can rewrite things like this. Now Mathologer regulars will be familiar with this maneuver. Everybody else, just think about it for a moment. Okay, all under control, great. So good, anyway, this gets the continued fraction going on top. Now 1 over 0.7320 is 1.3360 and so on. Now again from the start, how many squares of side length 1 fit into the green? Well, obviously 1, the integer part of 1.3360 and so on. Focus on the remaining green rectangle and rescale everything such that its short side becomes 1. There we go. Rewrite the top as before. 1 over 0.3360 is 2.7320, etc. How many squares can we cut off the green? 2, of course, and so on. As you can see, the sequence of numbers that corresponds to the spiral is exactly the sequence of numbers in the denominators of the infinite fraction. And with this transition to simple continued fractions understood, you're ready for the Mathologer video dedicated to continued fractions and some of the other amazing insights they offer into the nature of numbers. For example, the amazing pattern in the continued fraction of the number e, the continued fraction of pi, and the curious observation that the golden ratio, the number with the simplest spiral and continued fraction, is the most irrational number, etc. And that's it for today, except here's one more puzzle. Apart from the golden spiral, what else is wrong with this picture here?